Yeah, thank you for coming. Pleasure to speak here. So it's about exactly once. So what I want to do is, first I want to explain what exactly once means. What guarantees it provides, what guarantees it does not provide. And then I want to talk a little bit about stream processing, failure scenarios, and why exactly once is so important. And then we're going to do a technical deep dive covering the Idempotent producer and Kafka transactions that provide exactly once processing guarantees in Kafka. I'm also going to explain how this is used in the Kafka Streams stream processing API. And yeah, so what does exactly once mean? And I would phrase it, exactly once means that the result of a computation, including all state changes, is the same if an error occurs during processing or not. I think this kind of high-level definition makes a lot of sense. And actually, I want to rephrase this a little bit and say, well, exactly once means if a failure happens during the computation and the computation is retried, the result is the same as if each record would have been processed exactly once. And there is where the term comes from. It doesn't mean, exactly once does not mean there are no retries. Retries must be done, but the result is the same as if no error happened and no retries would have happened. So why is this important? Well, stream processing is taking momentum, and stream processing nowadays must be exact. So if you say you go into the financial industry and you want to transfer money, you cannot transfer money twice, you cannot have duplicates. And Apache Kafka is the heart of the streaming platform. And nowadays, or before exactly once, a lot of people put a lot of effort on top of Apache Kafka to make the application exactly once. So the point is, if a lot of people need it, it's much better that Kafka directly provides those primitives because it makes the application code simpler. And also, if it's implemented only once, most likely we have less bugs in it, or hopefully none. And so the overall stack is getting simplified. So now, if you want to do stream processing with Kafka, what does it actually mean? So the overall pattern in stream processing is to say you have some input topics, you do some computations, and you write the result to some output topics. And usually the computation is expressed as a DAG of operators. Here we have an example with like a couple of source operators. The one in the middle might be a join or a merge. And then we have some things that are writing to the output topics. Now the important thing is modern stream processing operators can be stateful or stateless. And having state makes the computation much more powerful, but it's also more difficult now to actually provide exactly once guarantees, and we will see why. And the last point is that you also have to track your progress on your input topics. So what did I read and what did I process? And if you do stream processing and you have a record, well, you would get an input record on a topic. And since the input record would be flowing through your DAG, the local states would be modified. And then finally, you're getting an output record in your output topic. And as a last step, you would mark the input record as read and consumed, and you move forward to wait for the next input record coming in. Now that's a high-level view how stream processing works. So now the question is, well, we talked about failures already. What could go wrong if we do this? And there are three error scenarios I want to show here. And the first one are the classical duplicate writes. So let's say the computation is in this state. The input record was consumed. The states have been updated, and an output record was written. Now something goes wrong, and the application does not recognize that the output was written correctly. So it would retry the write, and while retrying, a duplicate would be introduced. That's something, of course, we don't want to have. That's the first scenario. The next scenario would be duplicate state updates. Similar scenario, we are a little earlier in the computation, So the record was processed partially, state was updated, and now in this maybe join operator, something goes wrong. So what stream processing does now, well, mentioned already, we are retrying. So we're going back and we are feeding the record into the topology again. But now the point is the state was already modified. So when we now do the computation again and read this input record, because we have a different state, we might actually produce a different output record now. This different output record would also update the second state differently and finally end up in the output record as a modified record, not as a red record we actually want to have. Second scenario. Then we have a third scenario. Similar to the first one, we have processed the record successfully. It was written to the output topic, all good. And now we want to mark the input record as red. And this could all go wrong. And if this happens, well, we would also fall back and reread this input record. Now both states have already been updated, and the output record was also written. And that means when we reprocess this record, well, state modification is different again. We might again produce a different output record, and finally write, it's not really a duplicate, but it's something we don't want to have. So it's kind of a duplicate, but it might actually have a different value. And so to sum this up, if we want to do exactly once processing, we need to do all or nothing of those three things. On the one hand, we need to write the results to the output topics. On the other hand, we need to update our state. And we need to mark the input as consumed. If we now go a step back and look at how Kafka Streams is actually doing this, then we have to notice a few things. First of all, we have our local states that might get updated. But in Kafka Streams, those local states are actually ephemeral. They're performance optimization. And the source of the truth is a changelog topic, so we are writing in the back. That's quite similar to what we have heard in the keynote today. At any point in time, you can blow up your application state, and you can recreate it from those topics. And that is what Kafka Streams does. On the other hand, we said, well, we also need to take care of the progress on the input topics we're doing. And as most people know, in Kafka, it's also called committing offsets. And that's also tracked in a specific topic called the consumer offset topic. And with this in mind, and going back to saying, well, we need to do all or nothing, we can actually translate those three statements and saying, well, writing all results means writing to output topics. Updating all states means writing to changelog topics. And marking input as consumed means writing to offset commit topic. So basically, we can break everything down to a single operation, writing to topics. And if we can do this in an exactly once manner, then we can do exactly once stream processing. Okay, so what does it mean in more detail? First of all, we have the write path. We have seen that we might introduce duplicates. And to avoid duplicates, we need an idempotent operation. And that is what the idempotent producer offers. On the other hand, we are writing to multiple partitions at the same time. So we have seen three different types of partitions or topics: output topics, changelog topics, and the offset topic. So we need to ensure that we can do these writes to these multi-partitions in an atomic way. And that is what Kafka calls a transaction. And then on the read path, we also need to do some cleanup. Transaction can be committed or can be aborted. So if a transaction gets aborted, we need to make sure that those data is never delivered to the application when those topics are consumed. And then we have to stitch this all together. And we need a transactional read, process, write pattern to get this all in a stream processing fashion. So let's talk about idempotency and how this works in Kafka in detail. So topic partitions in Kafka are append-only logs. And before exactly once, there is a producer sending data to those topics. Here we have key value pairs, ID 1, ID 2, with some values, and we're doing an additional send. The broker appends this message to the topic, as expected, and sends an acknowledgement to the producer back. And this acknowledgement could get lost. And that would be a source of a retry and a duplicate. So why can it get lost? Well, there are multiple different scenarios. The network itself might lose the message, that's possible. The broker might go down right before it sends the acknowledgement. And there are all kind of other different scenarios. It's a distributed system. So if now the producer does the retry, well, it appends the broker appends the message a second time because it does not know that the producer is doing a retry. Broker has no notion before exactly once to identify this. And then, yeah, we are ending up with this duplicate here. So with the idempotent producer, the protocol here was a little bit changed. And also the data that is sent is a little bit changed. So each Kafka message is getting 2 additional fields. One is the producer ID, noted as PID here, and the other one is the sequence number. So what we see here, we have the same producer. The producer has the producer ID 100. That's a unique ID over all producers in the cluster assigned by the broker. And now the producer sends those messages. And for each message, it increases the sequence number. And the broker does the bookkeeping of those sequence numbers as well as the producer. So now when we send this next message with sequence number 2, the broker says, well, the last sequence number is 1. That is what I expect. And I append the record to the log. The acknowledgement goes back again. Again, we might have an error scenario. But now when we do the retry, the broker will not append the message again, because the broker can identify the duplicate based on the producer ID and the sequence number. And this makes the operation idempotent. And so if you use this feature, as long as your producer is healthy, you don't have to do any extra coding. You will never get any duplicates. It's also pretty simple to use because you just have to enable a configuration and you don't have to make any code changes. So by default, it's disabled so far, but there are even discussions to enable it by default. And you also need to change some other configurations. So for example, you need to set acknowledgements to all. And of course, you need to configure retries in the first place, because if you don't have retries and if something goes wrong, you might even lose data. So to sum it up, Kafka's idempotent producer means broker-side deduplication, and all the information that is required to do the deduplication, like producer ID and sequence number, is stored directly in the log. So it's also replicated, so you will never lose this information. That's very important for error scenarios. Okay, so going back to what could go wrong, duplicate writes, okay, covered with idempotent producer. So what can we do about duplicate state updates? So remember, what we want to do is all or nothing. We want to write to output topics, changelog topics, and those offset commit topics. And I talked about this before already. We basically need a multi-partition atomic write. And that is what Kafka transactions offer. It's based on a two-phase commit protocol. And now you might think, well, distributed two-phase commit protocols, that sounds pretty heavy. The way Kafka builds it, though, is actually pretty performant. I don't want to say it has no impact, but it's not as big as you might see. And so Kafka transactions, if you use them, still have a very, very high throughput and low latency. So how do those transactions actually work? So let's say we have a producer, and this producer is writing to multiple different topics and different partitions. In this example, we have 2 topics with 2 partitions each. On the broker side, to manage the transactions, there will be a transactional log. So when the producer wants to start a transaction, first it does a begin transaction to initialize the transaction and to tell the broker that a new transaction begins. After that, like in the code before, you would do some send calls to append some messages. And here in the example, we are writing 4 messages to different topic partitions. In the transactional log, we see that all those topic partitions are actually mapped and added to this transaction. That is, it also has a transactional ID. I will cover that a little later. okay, now we have written everything to the log, and now we want to commit the transaction. So we now call commit transaction. And that triggers the two-phase commit protocol. When commit transaction is called, the first thing is it is ensured that the producer is flushing all writes to the broker, and it's also ensured that all replication on the broker is done. So data is there reliably. If that is done, this prepare commit marker is written to the log, and if that is successful, the transaction is successful. It's not finished, but it's successful. So it's a classic two-phase commit. So that means if now something goes wrong, we can always finish the transaction and roll it forward in a successful way. Then the second phase of the commit is basically now we really need to say, well, we need to finish the transaction, and for that, commit markers are written to those topic partitions. After those commit markers are written, those messages are now actually able to be consumed by a consumer. Before that, they're not consumable. And if that was successful, then a final commit is written to the transactional log, and now the transaction is really finished. We see that's a little bit more complicated to use because you have to change your code to use it. But it's also from an API point of view not like too complex. You have just have a begin transaction and a commit transaction at the end. The other scenario is, well, you also might want to abort some data. So how does this work? So similar scenario, we are starting a new transaction using the same producer here, and we're writing more records to the output topic. In this case, M5, M6, and M7. And now we're saying, well, we don't want to actually publish this data, so we can just call an abort transaction. This triggers a similar mechanism, but now instead of commit markers, abort markers are written into the application log. So if we have this scenario, so how can we make duplicate state updates? How can we solve this? Again, recap, local state is only a cache for us, so we can ignore it, and we're looking at the changelog topics. So when we have an input record that is processed and state is updated, it's actually a write to the changelog topic and sending down further records for processing. If you have the same error scenario as in the beginning and something goes wrong, well, what we do is we abort the transaction. So an abort marker is written to the changelog topic, and so the changelog topic still represents the old state. It's like unmodified. Now when we reprocess the record, because the state was not really modified, on reprocessing we do the exact same computation as before, and we get the exact same result as if no error would have happened. And with this mechanism, we can actually checkmark the second bullet point. Duplicate state updates are also covered. Now we have the last point, reread the input. And here I give a little bit a more high-level picture. So again, we have some input topics, and we do some processing that might also include some state changes. So the producer, and in this scenario now, we are not only good to have a producer, of course, we also need a consumer to read the input data. So far, I only have covered the producer. So if we do this, well, first we would have a producer and start a new transaction. And then we would also use a consumer to pull data from the input topics. And a standard pattern in stream processing would be, or in processing in Kafka in general, well, you loop over those records, you do some processing, and you might produce some output results to the output topics. Okay. Now, if all this is successful, we actually now want to commit the offsets of the consumer. And in order to make all this in a transactional manner, now we don't use the consumer to commit the offsets, but we use the producer. After all, writing to or committing the offsets is a write to a topic. And that is something the producer can do, and it actually offers a special API for that. Send offsets. So you would take the current offsets of the consumer and feed it into the producer, and afterwards we would commit the transaction. And this ensures that the offsets are only committed if the transaction is committed. So if we write all our changelog and output records, and we write our offsets, and we commit everything, then the offsets are really only moving forward if the transaction is successful. If we abort it, those commits to the offset topic would never make it, they would be aborted, and then we can go back with the consumer and avoid duplicate reads, because we know what the old offset was. So to put this together in this picture we have seen already, again, we have the record was already processed. We have written data to the changelog topic. We have written data to the output topic. Now we try to commit. So we're basically writing the one to the consumer offset topic. Now something goes wrong. So now we abort everything. We're getting abort markers all over the place. So now we're in the exact same state as before the transaction started. So now we can reprocess the same record. And we also have recovered our state. And we're getting the exact same output as originally without any modifications. Now again, we are trying to commit the offset again. This time it's successful, and we're getting commit markers over all those topics at once. This also solves the problem about rereading input. And that means now we basically have achieved this all or nothing pattern we want, that we write to output topics, to changelog topics, and to the offset commit topic all at once. So now you might ask, what about those dirty reads? So we have seen, even if we have rolled back a transaction and aborted something, there are still those additional messages in the topic. And for this, Kafka adds a transactional consumer. So that is the topic we have seen before. We have some messages written that are committed. We have some messages written that are aborted. And if the consumer is configured to be transactional, the consumer would only deliver data to the application that is actually committed. In this scenario, it would be M1 to M4. So the messages M5, M6, and M7 actually are aborted, so they're not delivered. The other important thing to notice is we also have this message M8. And this message is neither aborted nor committed. So it's part of a pending transaction. And it's also ensured that this message is never delivered to the application. Using this is also pretty simple. There is just a configuration you need to change. It's called isolation level. By default, it's set to read uncommitted. But you can just switch it to recommitted, and then you don't see any of those. Another thing is the commit and abort markers are also hidden. Basically, they consume one offset in the topic. So that is something you need to be aware. If you read, you don't have consecutive offset anymore because there are those markers in between. The other thing is also when you consume, because those markers are hidden from you, you don't even know what data are you consuming or to which transaction a message actually belongs to. So that's completely transparent, and that's the way it should be, because if you consume, you should not need to care about those transactional boundaries. And it's also similar to transactions in a database. If a transaction updates the database and later you read, well, you don't really know which rows were updated before from which transaction or not. So that's pretty similar. So to use those transactions, I mentioned already this transactional ID. That is something you need to configure on your producer. And the transactional ID must also be unique all in the whole cluster. And that's something the developer needs to take care of to assign this unique ID. By default, it sets to null, so transactions are not enabled. And it also requires you to enable idempotency because, well, if you have transactions, but you still might have duplicate writes, well, you're out of luck, of course, because we want to do exactly once. So idempotency is, of course, a pre-requirement. So to summarize this, transactions in Apache Kafka are not the same thing as database transactions. It's an atomic multi-partition write. and it's based on a two-phase commit protocol. And this design makes it so powerful because multiple transactions can actually run in parallel, and they do not block each other, because also producers writing in parallel can just append their records, and there is no locking going on, basically. Only if you do the commit, some synchronization point happens. So now going back to Kafka Streams, with Kafka Streams, it's actually even simpler to do all this, because now I explain the producer and consumer API. So you can build all this in your own application. But with Kafka Streams, you only just enable it as a config, and you don't have to change your code as well. And then Kafka Streams takes care of all the details about committing transactions, about the management of the transactional ID, and also about state updates. And that makes Kafka Streams actually the easiest way to use exactly one stream processing with Kafka, because, well, you don't have to do much. Now, you might ask, well, I've talked about a single application, and what if I want to build end-to-end pipelines? Well, as long as you stay in the exactly one zone, I want to call it, all is good for you. So if you have multiple applications building on top of Kafka, so like in a microservice deployment, exchanging data over topics, and everybody is using transactions, then you're completely safe. Of course, if you interact with external systems, then you, again, have to take care of some of those details, because transactions are within Kafka. It's not cross-system transactions. So to put this all together, since 2011, Kafka provides very strong guarantees with the idempotent producer and with transactions. And if the easiest way to use this is like Kafka Streams, that handles all the nitty-gritty details for you, but of course, the APIs are exposed at the producer and consumer level, so you can also integrate it in your own application if you want to. And the other thing is, using transactions, you have to rewrite code, but using just the idempotent producer is pretty simple because you don't have to change anything. And the idempotent producer in general is like quite lightweight, so the performance impact is also very, very low. I want to point to 3 more blog posts that give more details about exactly once. The first one is more like a general blog post. The second one covers details about transactions in Kafka. And the third one focuses on exactly once in the Streams API. And with this, thanks for coming, and I'm happy to take any questions.
Microphones for those who want to ask questions. Raise your hand and I'll hand you a microphone.
Hi. You talked about producer IDs. First, how they calculated and how do they survive a producer restart? Because if they don't, and then the producer restarts, then it's going to come up with a new producer ID and then maybe send the same message, which will to Kafka will look like it's another message, whereas actually it's the same one.
Yes, that's completely true. So producer IDs are generated by the broker. So and if the producer dies and loses the producer ID, then the broker is not of any help anymore. So the producer must survive in order to reuse the same ID. What you've said that the producer might get a new ID is completely correct. And for this case, if you only use idempotency, you have to do some more additional handling to make sure you don't introduce duplicates. Because those duplicates the idempotent producer basically guards you from are only internal retries. So if you do a producer.send and you do producer.send again, it's 2 different messages. And that is something idempotency cannot solve for you. But it's a little similar to transactions, actually. If you say you do a start transaction and then you die and you do a abort transaction, you still need to find the latest point to set up and initialize your application again. And that's the same thing for the idempotent producer.
So I had a similar question. So what is your recommendation for doing that? Because if the producer dies, right, or gets restarted, how we handle this case? Because basically producer forwards our messages. If he dies, he will try to forward this message again. This message can come from Postgres or any other data store. Do you have a scenario for that? And similar question on the consumer side. So after I'm consuming the messages at the end, after receiving it from the stream, I'm also storing state in some other data store like Postgres or Mongo or whatever, right? And we don't have a distributed transaction on this data store and Kafka commit. So how to handle those situations?
Yeah. So for the second part, if you communicate with an external system, if this system basically gives you a transactional API, something like state whatever database, then what you can do actually is to say, well, instead of using the consumer again to commit my offsets, I add those offsets to this transaction, write it to the target system. And then when you restart, well, either your writes to the target system, including those offsets, were successful or not, and you get the latest offset from the target system. Then you cannot, exploit Kafka's commit mechanism for offsets anymore. It's a similar thing what we are doing here. We also add it to the producer side, and basically your producer side is a write to the external system. And yeah, for the first question about how to handle this, that really depends on the application. So if you would have kind of an ID that you can identify a message, then you would also need a consumer maybe to say, well, if I restart, first I need to figure out what is my latest consistent point. So maybe you need to read some data back, and then you can initialize your producer correctly. But yes, that's some manual effort. So keep in mind, those transactions are built for a read process write pattern in Kafka. So if you only have the write path or only have the read path, then that's exactly this slide, then you're on the border of the exactly one zone, and then you need to do some additional stuff on top of that. Kafka only has the read process write pattern covered for you.
Yeah, question. So for the high-level DSL APIs, how basically, let's imagine you have applications that consume some messages, produce some messages, and how does it know when exactly do we commit transactions? So I would imagine that you need some kind of markers on the high-level DSL API level for this.
That really depends on the application. On the one hand, on the other hand, it's actually more like a performance optimization, how often you want to commit. So if you put transactions aside and you're writing to the topic, well, if you just produce, well, you don't have any boundaries what you produce. And if you have like application level boundaries, could say, you don't need to align those boundaries necessarily with the transaction. You can. It's like also committing offsets when you consume. If you commit offsets more often, you have more overhead than if you don't commit offsets. And if you commit too often, well, you might have lower throughput, because committing a transaction is a heavy thing. As long as the transaction is in flight, the overhead is more or less zero. Only when you commit, you get overhead. And the other thing is, because data is not delivered until it is committed or aborted, you get higher latency if you commit not often enough. So there's this kind of trade-off, and that's something, well, application specific.
Okay, so it means that from the Kafka perspective, it is just a bit different perspective of what we call transaction, right? From the Kafka perspective, transaction is just transformation from input to output. But from the application perspective, it may be collection of input messages that we want to be produced and delivered from the service as a, let's say.
Yes, that's not covered. Yeah.
Okay.
Because at the application level, you don't see the transactional boundaries. So you cannot say, I have 3 input messages that belong to a transaction, and I process them at once and then I commit. Because even on the input side, you don't even know that those messages belong to the same transaction in the first place.
Yes, that's right, but okay, thank you.
How do you resolve the ordering of messages? Like if one transaction is kind of delayed in committing and the messages were produced in an interspersed way, how do you decide what the ordering was, and how do the consumers have to like go back and rewind and replay the messages from the later committed transactions? And
yeah, no, the ordering does not change at all. So because when data is written, similar before transactions, if you have multiple producers writing to the same topic, messages are interleaved. For a single producer writing to one partition, it's strong in order per partition delivery guarantee, and that doesn't change. So that means if we don't have the commit markers here, and now a second producer comes and appends messages, they will just be appended. And then it's just like 2 different transactions in flight, and when the first transaction gets committed, then those data can be delivered. And the messages of different transactions can even interleave. It does not really matter. And Kafka takes care that only messages that are finally committed or aborted are actually ready to be delivered. And with regard to ordering, nothing changes. It's still the same.
so could a consumer consume messages from the first the transaction that was committed, and then the second transaction is committed, but it included messages with earlier offsets than the consumer's already read?
So if you have multiple interleaved transactions, the consumer would consume those messages just in offset order as before, and the consumer doesn't even know that they're belonging to different transactions. I mean, internally it can track it, but on the application side, you just do a pull, you get those stream of messages, you don't even see it.
Okay.
Yeah, sorry, I had a similar question, but I still don't get your answer about the interleaved transaction. So is the commit marker somehow including the messages that were written as part of that transaction? And indeed, as the previous guy also asked, can you then not get out of order message delivery, or at least older offsets are being delivered in the next poll? Because the commit of that second transaction comes later than that first transaction.
Yes, that doesn't really matter. So the only thing that determines the order is the order in which the producers are appending the messages to the log. Yeah. That's the same as before. So now if you have 2 transactions interleaving and both are committed, but you would just read the data in the same order as they are written. And it's a little bit more tricky if one transaction is not committed yet.
That's what I mean.
For this case, basically, you would say, and that's what Kafka calls the last stable offset. It's similar to the high watermark that is tracking the replication. And the last stable offset marks the last message that was committed or aborted. So basically, when those transactions interleave, you would only read from the first transaction to the point where the second transaction starts, and then nothing you would block until this transaction also aborts or commits, and then the consumer would get more data.
Okay, thanks. Yeah, that was missing.
Yeah.
Thanks.
So one bogus producer could block the entire system, the entire department.
That's true. For that, there is also a timeout. So transactions can time out. So if a producer has an open transaction and dies and never comes back, eventually it will just be aborted, so that the system does not block forever.
Time for one more question over here. And you can always catch Matthias later on in the show floor.
So in the original flow, you assumed that the content of the message can get changed depending on the state of like one of the systems that is processing the message, like if we change from red to green, right? So later on, if we change this into like writing messages into the changelog, that means that if the next message comes in that should act on the same piece of data, let's say, it will not see the latest state because that state is still not committed. It's like somewhere in the changelog and it's acting on stale data. So how would that work?
It depends on the implementation, of course. If you have a local state copy, you of course need to clean up your state to get back to the old one.
Well, yeah, but let's say you want the new state, like you just processed an update that updated the state to something new, and then the next message comes in that wants to act on whatever the freshest state is, right? But
I mean, if the change gets committed, of course, the state is reflected.
Oh yeah, but it's still in the pipeline. It's still going through the next stages or whatnot.
I'm not sure.
Well, like let's say the message like went through the first stage and it turned from, let's say, red to green, right? And then the next message comes in that should act on the same piece of data, and now the state of this system that was processing it has not been updated yet, and it's acting on the state
in this case, basically, the second message would work on the updated state, and if the first message fails, well, we would reset both messages to the old state and retry.
Okay, so it would see the new state.
Yeah, totally, yeah.
All right, yeah, thanks.
Thank you, everyone. Thank you, Matthias. And don't forget to fill out your session form.